Hey, welcome back. Momentum and impulse. We're going to take a look at how we can define both of these concepts, and we're going to find that, of course, that if we're talking about motion, that there's usually an applied force of some type, which means you have unbalanced forces. If something's in motion, there's been some unbalanced force overall. So we've got net forces equaling something unbalanced, so there's motion in a particular direction. And we just have to define that direction, and that's how we know if we have positive or negative values. So let's just jump in, take a quick look at momentum and impulse. Keep in mind that everything is about vectors, and it's all about direction as far as assigning value to the magnitude, whether it's positive or negative value. Let's take a look. Hey, welcome back. Just a quick short video, make this as quickly as possible. We're going to look at two concepts that are sort of the kind of loosely we can say are two sides of the same coin. They sometimes are used interchangeably, but we want to differentiate between the two. Those two concepts are momentum and impulse. And so in physics, it's always a good idea to always put yourself in place of the motion, because since we associate what happens in our world with how we feel. If you look at a word problem, if you look at something that's being presented in physics, in lab, whatever the case might be, and you put yourself in that position of the motion of that object, you can sort of reflect, how would I feel if this were happening to me? And then you have a pretty good understanding of how things are changing. You can feel when things are speeding up, slowing down, and then we can start applying all those concepts like acceleration. There was a force applied. There was a force that was a pulling force, whatever the case might be. And of course, time is always a part of everything, because if there's motion, some sort of time is going by. So with that said, let's take a look here. How can we define the concepts of momentum and impulse? So momentum, okay. So it's important to think about momentum from the concept of force. So if you just think of momentum in every day, you can say, wow, you can be watching, you might say something like, I need to get some momentum in my for today. I need to get some momentum going. I'm moving kind of slowly today. Well, in that sense, you're not necessarily thinking about it mathematically, but you are applying something that does make sense. You're talking about changing how quickly you're doing something. So you're adding some momentum. So in other words, you're increasing the rate of which you are doing something or are not doing something. So there can be an increase or a decrease. So with that said, we can think of momentum. Let's go back to our concept of force. Okay? So we know force, we've got mass times acceleration. All right, so now let's break this down. We know acceleration is a change in velocity over a change in time. Okay, so now let's just bring our mass variable down. So now we have this, right? So now we're looking at force equals mass times change in velocity over time. So let's clean this up a little bit. Force equals mass times the change in velocity over the change in time. Okay. All right. This is easy. This is the easy part. Let me just highlight this real quick. That right there, that is the definition of momentum. All right. So right here, oops. If we, there we go. So right here, mass times the change in velocity, that is the definition of momentum. And this is momentum, okay? So momentum, it tends to be written with its own variable, and that is a lowercase p, okay? Momentum is a lowercase p. And so momentum equals mass times the change in velocity. This literally is, that's the equation for momentum, mass times velocity. And so you can see here that when there's a force applied, that mass will begin to speed up per some unit of time. And we see here, right, we see here that we've got, as you apply a force, that the mass will speed up per some unit of time. Makes sense. All right. So now we ask ourselves, what's the unit for momentum? Well, to do that, just go back to the definition, which is the equation. So the equation is the definition, and the definition is the equation. If you begin thinking like that in physics, it makes it a whole lot easier. It did for me anyway, and I don't know how else to really approach it. You can try memorizing textbook definitions all day long. It's not going to do you any good. All right. Well, here's what we do. What's the unit? Well, we know the unit for mass. We go with kilograms, because when we're looking at force, we know we have kilogram meters per second squared, right? Well, the unit for velocity is meters per second. Those two units side by side means you multiply them. So literally the unit for momentum is kilogram meters per second. So it looks a whole lot like the force unit, but in force there is acceleration, right? So remember, in force we've got acceleration like we have up here, and that's meters per second squared. What we did was derive out of the acceleration the change in velocity from that, and so we're just looking at the velocity part of the acceleration itself. And when we do that, it's isolating it out, and so we no longer have that second unit. That seems kind of weird to say, but it's true. All right. So let's move on and let's take a look at impulse. Oh gosh, this coffee is delicious. It's still Italian roast. I don't know which video you watched last, but either I'm drinking French roast, Italian roast, or some blend of the two. Either way, absolutely delicious. All right, so now we have impulse. Okay. Just come up with some neat, organized way of doing your stuff. All right, so the impulse literally is the change in momentum. All right, so impulse by definition is the change in momentum. So this is where it can get a little confusing. So if a force is applied, then and something moves, then remember from some previous lessons, you have an unbalanced force. So if something goes in motion, then that means the force that was applied that pushed it in that direction was greater than the force pushing back in the opposite direction. Here, let me go this way. If you push in this direction, then there is a force in that direction, and if the object actually moves in that direction, it's greater than the force in that direction, the opposite. So it was an unbalanced force, and so the object moves, right? We know this. Now, within that, looking at momentum, we realize momentum is that change in the velocity of that mass. But as it's moving, think of something rolling. It's not always rolling with the exact same velocity. And so at any given point in time, what you can do is you can look at what is happening with the acceleration due to that force, and that right there is the impulse. So let's go back to our equation. What we know is we have a force that is applied, right? So now if we think about it right here, if we think about it right there, mass times velocity, sorry, I forget to turn that off sometimes. That is our momentum, right? That is our momentum. So if you think about it, the mass times velocity that's right up here on the top, that is a change in momentum per a change in time. So by understanding the concept of it, we can derive another form of an equation that is useful. And so that is the trick in physics, is not necessarily just memorizing or plugging and chugging values into an equation. It literally is just thinking about the concept of the situation. And if you do that, if you put yourself in the place of that, I think it makes it a little bit easier. So if you've got a force, then there's a change in momentum per some amount of time because there's an unbalanced force, right? So all this, remember, is due to unbalanced forces. All right? So if we think about this, let's rearrange this equation to isolate just momentum by itself, right? So if we did that, we know we would multiply both sides by delta t. And so we would get the change in momentum equals force times time. All right, force times time. And this force times time right here, that right there, this is our impulse. That is, so the change of momentum at that point in time due to a force caused it to move. So think of, you've seen like EKG readings or whatever, that might be one way to think about it. As these things, as you've got something moving, real quick there's a quick jump and a quick jump and a quick jump and a quick jump and a quick jump. At that point in time, there is a change in momentum that causes that movement to change, right? And so now you ask yourself, well, what's the unit for impulse, right? So let's take this part here. Force, we know, is a Newton. And newtons, oops. All right, and then time, you know, is seconds. All right. So now let's think about this. A Newton is kilogram meters per second squared. So force times time means you're multiplying those two things together. So we're actually multiplying this side by seconds. So you can see that a seconds unit is going to cancel out, and we're going to be left with kilogram meters per second, which is the exact same that we had over here. And it makes sense, since impulse is a change in the momentum. It makes sense that they would have the exact same unit. All right. So there is the basics between momentum and impulse. Now we're just going to apply it to something that kind of makes some sense. Let's take a look. All right. So momentum, we know what that is. We need to now start asking ourselves, what does it mean if momentum is conserved? Well, when something is conserved, it kind of means that it's kept, that it's not lost, for lack of better words. I mean, energy is neither created nor destroyed. You don't lose any energy, but lost means that we can't account for it, right? So we've got two objects. So what does it mean that the momentum is conserved? So if we think about this, if we have two objects, that means object one has momentum. And we know that momentum is mass times velocity. So we technically could put a 1 here, and we could put a 1 here, just to denote that it's the mass of the object 1 and it's the change in velocity of object 1, right? So then we have change in momentum of the second object, so it begs reasoning that we would put m with a 2 and velocity with a 2, right? So we go the second mass times the change in the velocity of that second object's mass, right? Okay. If it's conserved, what that means is that object 1's momentum equals the momentum of object 2. The reason for this is think about when things collide. So when things hit, those are two objects. When they hit with force. But we've already looked at the fact that with force, there's a change in momentum. So something is happening between the objects. Remember, we're having unbalanced forces here. But the total momentum, everything involved with the motion and the movement between those two objects equals out. So think about it this way. I mean, sports analogies are they're cliche and probably overused, but think about it this way. You've got two runners, two players. They're running at each other. One of them is moving kind of slowly, running kind of slower than the other. This one over here is running much faster. There's going to come a point where they collide. Now, based on how fast their velocity in a particular direction they're going, when they hit, the two of them are going to, we know, bounce off of each other in some way, shape, or form. But they both are not going to bounce off of each other and maybe travel the same distance. And the reason for that is because since they were moving with different velocities, when they collided, that means they applied different forces that were unbalanced, And then as those forces were redirected back, those forces became unbalanced. However, they are conserved and all of those forces equal out to each other. All right? All those forces equal out to each other. So what that means, if you think about it, you have this runner here, you have this runner here. If you add the two together, it balances out. But we're talking about vectors, right? Force, acceleration, which means you have direction. So if you think about it, this runner is running in a particular direction that you could call positive or negative, and this runner is moving in a direction you could call positive or negative. If the forces, if the momentums due to the force equal out to each other, well, one of them you have to assign as positive, and the other you have to assign as negative according to our coordinate system that we have, right? So what that means is the momentum of one plus the momentum of the other has to equal 0. It has to equal out. The change in the momentum of them both. It has to equal out. It has to equal out. So now let's think about this. All right? This is where we're getting into conservation. All right? Conservation. So now we said that one of them is going in this direction that we might define as positive, and this one's going in this direction we might define as negative. It doesn't matter which one is 1 or 2. It really doesn't make a difference, other than when you assign what is positive and negative in how you present the information. Okay? Because we typically think, to our right is positive, up is positive, down is negative, to our left is negative, right? So we typically don't solve something to 0. So let's move this change in momentum from this side. So we've got the change in momentum of 1 would have to equal the change in momentum of the second object, but it would have to be negative if we brought it to the other side. And there you have it. Now, if we think about this, momentum is mass times the change in velocity, and that's number 1, equals, right? It would be a negative mass times the change in velocity of the second object. Now we don't have negative mass, so that's why I've put parentheses around the entire expression and then a negative sign, because you can't have a negative velocity, because that's just direction, right? It's a vector. And there you go. There's our conservation. There is our conservation. Now let's illustrate this. Here's a very classic example. All right? Here's a classic example. All right? I'm going to try to, sometimes I draw this well, sometimes I don't. Kind of looks like a gourd, but we're trying to call this a cannon. Let me see if I can. That'll work, and then it's got its little kickstand on it right there, right? So there it is. So inside there's a cannonball, obviously, right? So now let's think about this. Cannonball is going to fire something. It's going to fire, obviously, a cannonball that's going to take a path that's going to have a motion like this, and we'll talk about that motion. Now, this is something that leads us into the concept of projectiles. And then a cannonball is fired out of there. Okay, there's our cannonball. So now let's think about this for a second. Cannonball's right here. It's following this path right here. Bam, it's all the way over to there. It was in here, and the cannonball is fired, follows this path. The cannonball has mass. So does the cannon itself. The cannon itself, it has mass. It doesn't matter which one we call object 1, which one we call object 2, other than trying to define direction. Once we define direction, then that's when we typically assign our negative values, all right? But when you start it off, just put down what you know. And then worry about the negative signs after you've defined all your variables. So they both have mass, right? Which we know is measured in kilograms. That cannonball, it's moving at a certain rate, which means it has a change in velocity. Now, if you think about it, when the cannon fires, the cannon also moves. So the cannon has a change in velocity. Now, according to this diagram, the way we're looking at it, if we think about the way we define our coordinate points, we're saying in that direction is a positive direction. So according to this, everything we're showing here with the cannonball, all of this right here is a positive value. Now, if you think about it, when you watch that, what direction does the cannon move? Cannonball fires and the cannon moves in an opposite direction. So it makes sense we would assign that with a negative velocity. It's not a negative mass. Mass is mass. But the velocity is negative. So now if you think about it, if we wanted to, we could say that the change in momentum of this one, we could assign this as our 1, and we could assign this as our 2. Or you can call this 1, you can call this 2. It doesn't matter, but with the way, I'm just trying to be consistent with what we had up top, okay, up in the example. So we would know, we could see the change in momentum 1 would be according to its mass times the change in its velocity. Okay? And then right here, this obviously would be a change in momentum in the second object, and we would say its mass times its velocity. And this brings us right back to the fact that the momentum is conserved. Now, let's think about this. We can think about this quantitatively without any numbers whatsoever. The cannonball moves at a very high velocity, but it has less mass than the cannon. The cannon has greater mass than the cannonball, but when it moves backwards in the opposite direction with less velocity. It doesn't move as fast. If you begin to think about that, and we go to what we had up top, if we go back to what we had up here, then we begin to see that we have one of those mass variables that's greater, but wherever the greater mass variable is, it's going to be less of a velocity. And then the exact opposite is true for the other one. When there's a greater velocity, like with the cannon, then wherever the velocity is, right? So the cannonball has, I got tripped up on myself, sorry about that, it happens. The cannonball has a lot of velocity and low mass. I know what happened. I'm looking at the screen and I got confused. Has low mass, right? But high velocity. Well, the cannon itself has a lot of mass, but it moves in the opposite direction with less velocity. It's always the opposite, and it makes sense. By that happening, it's going to conserve to where you're going to see that relationship happen. The total momentum will be conserved, and it will equal 0, which means that when you solve this problem here for something like this, you get the same value on both sides. Regardless of what the mass of the cannonball and the cannon are, once it's fired, because of the velocities, because of that momentum, that change of momentum, that impulse that is happening along every second of the change, it's going to equal each other. In the end, it's going to equal each other out. It'll be conserved, and the total change of momentum will be 0 because it's conserved all around. Change of momentum on both, the same change of momentum is the same on both sides, and the total difference, the net difference will be 0 because it's conserved. One side is positive, one side is negative. And that's really it. And we already know kilogram meters per second will be our unit. Think of a skateboarder, and that's another wonderful example. If you've got a person on a skateboard, if you've ever been on a skateboard and fallen off of a skateboard, then you know that if you fall off of the skateboard, you move in one direction and the skateboard flies off in another direction. Now the skateboard, it moves real fast, but it has less mass. You move backwards, but not as fast as the skateboard, and you have greater mass than the skateboard does. It's just like this problem here. The total momentum in that situation with our skateboarder falling off of the skateboard, the total momentum is going to be 0. It's going to be conserved in that system. And a system is just all the variables, all the things that are interacting together in whatever it is you're measuring. That's what we mean by a system. So I hope this helped. Watch the video again, do some of those practice problems. And everything will boil down to the conservation of momentum, the concept of impulse, and the fact that you've got a change in time, force, acceleration, mass, velocity. That's really, really it. And of course, time. Time's always involved with it. So it was good talking with you again. Go do those problems. I wish you luck, and I'll see you again soon. Stay curious. Good luck. Bye. There you go. Momentum and impulse. As long as you know the unit for force and you know the equation for force, it's very easy to pull back to realize that you can just sort of tease out momentum from that. Because if something, as you saw, if there's a force, if something is forced to move, then it suddenly gains some momentum. It's a fairly easy concept. The problems are really not too terribly difficult. We can always take a look at momentum or an impulse, which would just be at that point in time, what sort of force is being applied, and how does it affect its momentum, that change in momentum, that would be the impulse. Fairly easy concept. Work on those practice problems, and then, I don't know, stay curious. Drink some coffee. And I'll see you again in another episode. As always, it's great to see you, great talking with you. Bye.